Hello, welcome to this virtual organic chemistry lab. I'm Derek France. Today's lab is all about thin layer chromatography, TLC. And you want to take a look right here? That is what we call a TLC plate. So everything we do today is going to be done on plates that look like this. We have an aluminum backing right there, and in the front is silica gel. So silica gel in the front, thin. It's a thin layer of silica gel. That's why it's called thin layer chromatography. Let's begin by talking briefly about some of the theoretical considerations for this lab. Thin layer chromatography, or TLC, is a really important experimental technique in organic chemistry. Chromatography refers to separation of compounds based on their rate of flow through a medium. And the medium that we use in TLC is silica gel. Silica gel that is embedded on top of a plate. And this is our TLC plate right here. So what we do when we perform a thin layer chromatography is we put a line right about here, and then we put another line right about here, and we really just draw directly on the plate with a pencil. At a spot right down here, using a capillary, we're going to place a solution of the system that we're interested in. It might be a pure compound, it might be a mixture, but we're going to spot it right here. You're going to see this in the experiment. And then we let the solvent of that solution just evaporate. After that point, we're going to put a TLC plate inside of what's called a TLC chamber, which is just a fancy word for jar. Now that TLC chamber is not empty. It has a solvent inside. I'll indicate it like that. And that solvent can be essentially any common organic solvent. The polarity of the solvent will affect how high that spot moves. We're going to look more into that in just a moment. Through capillary action, the solvent down here will wick its way up the TLC plate. And then this top line is the line that we will stop it. So as soon as the solvent here reaches that top line, we will pull this TLC plate out of the TLC chamber, and our run will be completed. As the solvent moves up, it's going to cause this spot to move as well. And the distance traveled by that spot divided by the distance traveled by the eluent system will be something called RF, which is the retention factor. So just stating it one more time, the retention factor, or the RF, is the distance traveled by the spot divided by the distance traveled by the eluent. And this is affected by two things. It's affected by the polarity of the compound that we put in that spot, and it's affected by the eluent system, the polarity of the eluent system. So the balance of polarity between the spot compound in the spot as well as the solvent that's forming the eluent system both factor into the retention factor. It's important to note here that silica gel is highly polar, and being highly polar, it's going to more strongly interact with polar molecules than with nonpolar molecules. So if we imagine having a TLC plate like this, after we ran the TLC in the chamber, we originally had a spot right here. Let's just say that the spot traveled to here. The RF would be this distance divided by this distance. Now let's imagine that this spot right here in a different run, I'll put it as a red dot, that's where it began. Where would that end up if it was more polar than the blue compound on the left side? Because it's more polar, it's going to more strongly interact with the silica gel, and it's not going to move as far. So that compound, because it is very polar, is more polar, it's going to strongly interact with that highly polar silica gel, and it's going to move slower through the TLC plate as the eluent drags it up. What if we used a more polar eluent system? So in these two cases, in the left and in the center, we're considering that we're using the same eluent system. On the right side, we're going to use a more polar eluent system. And we can refer back to this original blue. So if we use this compound here, in this more polar eluent system, it begins down there. What do you think is going to happen relative to this spot? Is it going to be higher or lower? Is it going to have a higher RF or a lower RF value? Well, now we're going to have competing polarity between the eluent system and the silica on the TLC plate. And if you have a more polar eluent system, it's going to draw this material up, 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 up to a higher RF value. It's going to move faster in the more polar eluent system. So that's just a little bit of theory behind the experiment that we're going to do today. Now let's go back and get to work. You might recall in a previous episode of Virtual Organic Chemistry Lab that we did a chemically active extraction, and we saved a little bit of our original mixture in a vial that we labeled TLC Sample. We're going to be using this TLC sample, which still is in ethyl acetate solution, to determine what the best eluent system will be for separating the acidic and neutral components. We also got an organic acid. We were able to isolate this organic acid by filtration. It was placed inside of a filter paper wrap. I put a little bit in here. You can see how much I put in, not very much. And then we also had that neutral compound, which was an oil. We removed the ethyl acetate in the rotary evaporator. It's kind of hard to see, but there's one drop of that oil in here. So to begin, I'm going to just put a little bit of acetone in each of these vials. So now we have these vials. Our compound is dissolved in acetone in each of them, and it's a very good idea at this point to label these vials. I should have labeled them already. I'll label that vial N for neutral, and this vial A for acid. In the first part of the experiment, we are going to try to determine which solvent system is the best eluent for separating the organic acid and the organic neutral compound. So we have the original TLC sample right here, and we're going to use dichloromethane and methanol as pure solvents. Dichloromethane has medium polarity. Methanol is very highly polar. And then we're going to look at a gradient of ethyl acetate versus heptane. So pure ethyl acetate on the left side, pure heptane on the right side, and then in between we have 75% ethyl acetate, 25% heptane, 50-50, and then 25% ethyl acetate, 75% heptane. So we'll get 5 different samples here and be able to compare the separation of the spots as well as the RF differences between this set of heptane ethyl acetate combinations. Now let's take a closer look at the TLC chamber. You'll see that I put 4 milliliters of each of these solvents and the solvent systems in these TLC chambers. They're all labeled, they're capped, and in the back you can see there is a filter paper. So that filter paper is just hanging out on the back. Its entire purpose is just to saturate the air inside the chamber with the solvent system. I have also prepared TLC plates already to run in each of these solvent systems. I have put a line at the 1 centimeter from the bottom and 1 centimeter from the top. Now, how much sample do we need in order to develop a good TLC plate? We have our sample right over here, but we don't really know its concentration. It might be highly concentrated, it might be rather dilute. what we can do is we're going to be using these capillaries to spot. So we're going to take some of that liquid over there, and then we're just going to put a little spot right here, right on the line. But we have to kind of figure out how much we need. So if we take, just dip that capillary down into the solution. Here you can see that by capillary action, the liquid has gotten to right about there. And now how much of that should we put on the plate? I recommend beginning with less. You can always add more. You can never take it away. But I'm going to just put a little dab right there. And you'll see it looks wet. But that wetness will go away. That's just ethyl acetate. And that ethyl acetate is evaporating. So the solvent that is your medium to deliver your compound onto the TLC plate is not part of the eluent. We're going to wait for that to evaporate away, and it will not factor in to the polarity of the solvent system that you're using. So we're going to be eventually visualizing these TLC plates with UV light, but we can actually look at it right now with UV light. If you have the option, I'm zoomed in a little bit too close. I don't want to knock anything over. There we go. If you have the option between shortwave and long wave, we are going to use shortwave. So shortwave is 240 nanometer light, and when we shine it on the TLC plate, the TLC plate has an indicator. It has a compound that fluoresces when it's subjected to 254 nanometer light. The spot right here is absorbing that light, and because it's absorbing that light, it's preventing the fluorescence from the bottom, the compound that's in the silica gel, from coming through at that position. So if you can see a spot like that, that indicates you probably have enough material and you don't need to add any more for a TLC run. But let's look at what would happen if you decided that you weren't satisfied and you really just want to deliver this entire capillary to the TLC plate. So I loaded this up with more of our sample, and let's just put it all there. You can see we made a big dot. And hey, just for fun, why don't we just add more? This is going to be the what you don't do demonstration. So several things here. If you keep adding and you make a big blob as you add your sample, you are spreading out your compound all throughout that blob. And the bigger this circle is right here, the bigger the blob has to go as it elutes up and as it develops up through the TLC plate. The smaller it is, the smaller it will be, the better the separation will be. If you have a big blob there, you might actually be getting good separation, but you won't be able to visualize it because the compounds will just take up too much area as they go up the plate. So here you can see the comparison between these two plates. Now let's use dichloromethane to just determine if the first plate has enough sample on it. All right, so I opened up the chamber in order to place the sample inside. And we always want to, if the TLC plate is on the table, you can kind of move it around a little bit like that. But whenever we pick it up, we want to use the tweezers. So I'm going to get it off to the side of the table so I can pick it up. So this is our original sample, the original spot, which has what looks to be the right amount of material. And we're going to lay it gently down into the chamber. And I might be cutting it a little bit short by having that line at 1 centimeter from the bottom, because if I put this into the chamber and the solvent were to go above that line, not by capillary action, but the actual liquid solvent on the bottom, if that were above the line here, that would actually cause an extraction of our liquid out into the organic solvent, which would not be very ideal. That would not be something that we want. So you can see the solvent is by capillary action going up the plate. It looks wet. And now we're at the label. You don't want to move your plate while it's running. You want to make sure it's capped while it's running. But just for the sake of the video, I'm going to rotate here so you can see the line of solvent as it goes up. And through the miracle of video, I'll be able to speed this up as we run these in the video lab. During the lab, you will have to carefully watch them and make sure you don't overshoot that line. If you do overshoot the line, no problem. You can just draw a new line. Okay, that's not a big deal. But if that solvent goes all the way to the edge, if it elutes all the way to the very tippy top right here, that's going to be a sign that you're going to have to do it again, because you won't know where that edge of the solvent front actually ended. It could have ended here, and then 5 minutes later it's still here. You don't know. So you'll have to run it again. But just keep your eye on it. You have to look down. We can see it going up. And yeah, let's just watch that until it reaches the pencil line that I drew at the top of the plate. Okay, the solvent line has just reached the top line here, so we can open up our chamber, use the tweezer to pull out the plate, and there it is. So we're going to just let this evaporate for a little bit, let the dichloromethane eluent evaporate. Set it down, and now we're ready to visualize it. Let's see if it looks good. Do we get a good separation? Wow, look at that. A beautiful separation. So which compound do you think is going to have a higher RF, the organic acid or the organic neutral? We can have a hypothesis right now, but we'll have to actually run the TLC to be sure later. But that is beautiful, perfect separation. So let's see how the sample would look if we used this overloaded plate right here. All right, there it is. We have developed our overspotted sample. And here you can see we were lucky in this particular solvent system. We still get a pretty good separation, but these blobs are really big, and in most of these combinations of compounds, you're not going to get such a good separation. But our original spot, which look like this, we can use that. So the bottom is streaking a bit. That bottom spot streaks a bit, but there's just nothing we can really do about that. I've outlined both of these spots in pencil. So if I turn the light off, you can see where the spots are. And then from the center of those spots, using a ruler, you will be able to calculate your RF values for each one of these spots. It's very important, though, that you remember to start the ruler right down here at this line, not at the bottom of the plate. So based on what you see here, what is the RF value for both of these spots, for each of these spots? Okay, so we just demonstrated that dichloromethane is actually a pretty good solvent for the separation of these two compounds, of our organic acid and our organic neutral. Now let's go ahead and try all of these other solvent systems, from methanol and then this whole series of ethyl acetate and heptane mixtures. All right, let's analyze how well the separation worked. So the methanol, you might have noticed that that moved the slowest up as it was developing, and it's also going to take the longest to evaporate. So we'll look at that in a moment. But first, let's look at this series of ethyl acetate and heptane mixtures. So I'm just going to move the chambers back. So just to remind you, pure ethyl acetate is here, pure heptane is here. In the center is 50-50. This is 75% ethyl acetate, 25% heptane. This is the inverse, 25% ethyl acetate, 75% heptane. So we are increasing polarity starting here and going to the left. Highest polarity on the left, lowest polarity on the right. Let's take a look with our UV light. All right, if we begin right here, so heptane, pure heptane actually gives us a little bit of separation, but that bottom spot does not leave the baseline. So heptane isn't quite polar enough. The 25% ethyl acetate and 75% heptane gives a nice separation with two small spots. So that's looking really good. We'll look at that a little more in a moment. Over here now we have the 50-50 ethyl acetate and heptane. If we compare that to the 25% ethyl acetate, 75% heptane, the top spot hasn't changed very much. It's not that different between these two. The top spot isn't very different, but the bottom spot is much different. So the bottom spot on the right is nicely separated, but on the left plate, the bottom spot is merging with the top spot. So the separation here is much better on the right side than on the left side. And that trend will continue as we go to more and more polar. Here in the center is 75% ethyl acetate, 25% heptane, and then on the left is pure ethyl acetate. So we can see a spectrum here going from not polar enough to just about right, then too polar, too polar, too polar. But here's a nice view of that solvent system for the same compounds, how the different polarities will separate those two spots. Over here, methanol, remember methanol is our most polar solvent. So if we zoom in, it's just a big blob with a very high RF. So methanol is too polar. Methanol is the one here on the right. That's dichloromethane on the left. Methanol is just too polar. We don't get any separation. It takes all the compound all the way to a pretty high RF value. Okay, so here on the left, we're looking at the 25% ethyl acetate, 75% heptane TLC plate. And on the right, that is our dichloromethane TLC plate. So these both give good separation, give nice RF values of compounds right toward the center of the plate. But in order to now determine how well the extraction went, we're going to want to pick one of these. It turns out, in this particular case, either one of these could work for the next experiment that we're going to run. Because the RF difference is greater in dichloromethane, I'm going to pick that as our eluent for the next step of this experiment. Okay, so here we have our original TLC sample in the center, the organic neutral compound on the left, and the organic acidic compound on the right. So that was the solid, that was the oil, that was the original mixture, and the one in the center, that's the one that we've been running TLCs of this entire time. I have already delivered these samples as spots to the TLC plate. And if you look here, I tried to label it. It's kind of hard to draw on the TLC plate. You just you kind of etch off the silica, but I tried to write an N for neutral, an M for mix, and then an A for acid. I only have a mechanical pencil here. It's harder to draw on the TLC plates with a mechanical pencil. It's easier with a wooden pencil. And oh, there's an eyelash. Let's blow that, get that eyelash off the plate. Okay, it should be good. Let's look at it with the UV lamp just to see. We want to just make sure that we see spots there. So we have not yet put it in the dichloromethane. If you can visually see spots, and these are about the smallest spots that I could deliver, this should be good. We have to run the TLC plate. We have to develop it. If it turns out not to be good, we'll have to run it again. But for now, it looks like we have enough there that we can see it. So we will be able to see the spots after we develop the plate. It's also important to note that we use different capillaries for each of these samples. If you use the same capillary for different samples, you run the risk of cross-contamination. So you can use the same capillary for the same sample over and over again, but you definitely do not want to reuse the capillaries for different samples. All right, now we are ready to develop this TLC plate. Let's put it in dichloromethane. Cap the chamber, and if all goes well, this will be the last experiment we need to run. Okay, let's take a look at what we got. Let's just remind ourselves before we look at this new plate. This right here is the original TLC plate of the mixture. And we had 2 spots, and we want to know which of those spots is the acid, which of those spots is the neutral compound. Now we have our new TLC plate. Here is our new TLC plate that has all 3 components, the mixture in the center, the neutral on the left, the acid on the right. Let's take a look. Is that what it should look like? Does that look right? Yes, it does look right. So the central spot is the combination of the two, the neutral compound and the acidic compound. It looks just like the previous one that we ran. On the left side, we have the neutral. The top spot of the neutral, the only spot of the neutral, matches the top spot of the mixture. That confirms that the top spot is the neutral compound. The bottom spot, now you can see it has like that little bit of a streak. It's almost like a comet. We can see the top line doesn't match, but the bottom does. The top of the spot doesn't match, but the bottom of the spot does. So for the right side, the acidic compound matches the bottom spot of the mixture. So now we know the identities of the 2 spots of the plates. We don't know what those compounds are yet. We're going to determine that in the coming experiments. What we also don't see, let's take a closer look here. Note that on the neutral spot, we do not see anything right here. That, if we did see anything here, that would indicate the presence of the acidic component as an impurity. In the acidic component, we do not see any spot up here. If we did see something here, that would indicate the neutral component as an impurity in our acidic solid. All right, well, that brings us to the end of this organic chemistry virtual lab on thin layer chromatography. Thin layer chromatography, TLC, it's a very effective and cheap way to determine how many components are in a chemical mixture. It does have its limitations as well, but at least now we know how to use it, and it's a very common technique that organic chemists use all the time to determine how well a reaction is running, is the reaction done, is there any reactant left, is the product forming, things like that. In this case, it showed us that our extraction went really effectively when we did that. So now in the future, we're going to determine the identities of our 2 components, the acidic compound and the neutral compound. with TLC, we were able to see how well that extraction ran. All right, well, I look forward to seeing you again next time. I'm Derek France, and this has been Organic Virtual Chemistry Lab.